Draw mirror image isomers using projection formulas for any of the compounds that can exist as enantiomers. Let's look at that first compound. No chiral carbons. This carbon has 3 hydrogens, this has 2, this one has 2. We'll get back to this middle one because that's our best contender so far. This one has 2, this one has 2, and the last one has 3. But this middle carbon has a hydrogen, a bromine, and then 2 propyl groups coming off of it. And both propyl groups are identical to each other. So there aren't 4 unique things coming off of that carbon. It is not chiral. Same with the last one. That carbon has 2 bromines coming off of it. It's not chiral. The middle one, you have a chiral carbon. Off of this carbon right here, you have a hydrogen, a bromine, an ethyl group, and a bromoethyl group. So for that carbon, there's 2 mirror images we can draw. This one and this one. And these are our 2 enantiomers. This is the easiest way to draw the enantiomers. Draw one of the images, and then just draw the mirror plane and draw the mirror image, what it would look like in the mirror. A racemic mixture is containing equal amounts of a pair of enantiomers. So it's 50% one of the isomers and 50% the other isomers. Because the 2 isomers are rotating light in opposite directions, the overall effect is no rotation. And so racemic mixtures are optically inactive. Examples of chiral drugs. Here we have metoprolol, which treats high blood pressure. Pseudoephedrine, which is Sudafed, it breaks up congestion. L-Dopa, which is a dopamine prodrug, treats Parkinson's disease. Methylphenidate, Ritalin, treats attention hyperactivity deficit disorder. And all of them are chiral drugs. In general, only one of the optical isomers will be biologically active and the other one won't be. Stereoisomers. The maximum number of stereoisomers for a given chiral compound is 2 to the nth power, or n is the number of chiral carbons in the molecule. So if you only have 1 chiral carbon, there's only 2 possible enantiomers. You draw the first one, then you draw the mirror image plane, and then you draw its mirror image. If you have 2 non-identical chiral carbon atoms, you have 4 isomers. So here, we have 2 chiral carbons. And so we can have this isomer and its mirror image, and this isomer and its mirror image. So diastereomers are stereoisomers that are not mirror images. They are not enantiomers. And if a substance has 2 non-identical chiral carbons, this can happen. And so here we see 2 sets of enantiomers, but this one and this one are diastereomers to each other. They're not mirror images of each other, but they are stereoisomers. They are diastereomers. Let's look at another example. The 2N formula indicates that 4 stereoisomers of tartaric acid are possible. Formula 12 and 13 represent non-superimposable mirror images and are enantiomers. Because if we draw our mirror plane here, we see that they're mirror images from each other. And here, we see the other diastereomer and its mirror image. But this one, 12 and 14, would be diastereomers to each other. A meso compound is a stereoisomer that contains chiral carbon atoms that are superimposable on their own mirror images. And so here, you have 2 chiral carbons. This carbon is attached to a hydrogen, an OH, a carboxylic acid, and then this big group down here. And this carbon is attached to a hydrogen, a hydroxyl group, a carboxylic acid, and this big group. However, because there's a plane of symmetry through the middle of it, it's not optically active. It is not active at all, and it is a meso compound. The three stereoisomers of tartaric acid are represented in this fashion. We have negative tartaric acid, then the mirror image, positive tartaric acid, and then meso-tartaric acid, which we don't draw the fourth one with the OHs on the left because that would be the exact same molecule. You could just rotate it and get the exact same molecule because it is not chiral. How many stereoisomers exist for the following compound? We get 4, and that's what we'd expect because this carbon is not chiral. This carbon is not chiral. This one is, and this one is. So 2 to the second power is 4. You get 4 stereoisomers, 2 diastereomers, and that are mirror images. And again, none of them have a line of symmetry growing through them. These you might look at really quickly, but then you realize that they're not the same because down here that's a methyl group, whereas up here that's an ethyl group. So it's not exactly the same. There is no mirror plane that you can put through these molecules. There is no meso compound. If we look at this compound, we have a line of symmetry. We have meso structures. So we have the mesos is just one compound. This gives us 3 stereoisomers. Both meso compounds are superimposable on each other, and therefore they're the same compound. So this only has 3 structures, not 4. 2 enantiomers and 1 meso structure. And that is the end of the stereoisomer chapter.